So following on from yesterday and actually the previous sessions, they say we have already looked at hardware. We've looked a bit about the software. We've looked at how we go about replacing old system, and that got us also to the point where we started thinking, okay, what sits between the hardware and the software? What makes what gives us access how to use these hardware? And we noticed that the computer understand ones and zeros. So there are so many different kinds of hardware when it comes to the computer systems. Even if we take a system unit alone, we have things like sound card, we've got things like the USB, we've got HDMI, we've got the motherboard itself, you've got the processor. I mean, some of us are just learning more about how the processor work, let alone be able to use the software that we understand how to really interact with the software. So with the processor. So to make the use of hardware easy, so we don't necessarily have to really understand how each hardware interprets ones and zeros, or what kind of codec is required to make let's say sound card work, for example, or what kind of firmware is required for, let's say, a non-standard communication ports. Communication ports are things like the USB port and other things. And also for us to be able to use these softwares that we are using easily, or the application softwares that we use easily, example like PowerPoint, Microsoft Word, or Zoom, all those things. There is a software that sits between the hardware and the user applications that we normally run. And that software is called the system software. So the system software doing a lot of magic behind the scenes for us. So normally from the point where we boot the computer to the point that we actually shut down, we've got system software running in the background doing some magic for us to actually make it a lot easier for us to communicate with the hardware resources, or to use the hardware resources to run different applications at the same time, and then also pretty much to give access to the ICT resources. So in terms of objectives, yesterday we started talking about some of the things that we'll be covering in Probably Stead. We are likely going to touch about 3 of them this week, but we are likely to also go for a bit further. So question like, what is system software? And then we are interested in two types of these system software. We will think more about describing the function of an operating system, mostly because it's part of these two is one of these two types of the system software that we'll be looking at. And then we will look into what happens when you start your computer, from the point where you press the power button, or maybe when you press restart, or basically just booting your computer. Then we'll look at features of several standalone operating systems, so a bit more on operating systems by looking more at the standalone operating system. And by operating system, you've probably heard of at least one of them. Common examples of operating system: Windows operating system, Mac OS, and we mentioned a few things like the Android OS for embedded devices or mobile devices, you can say. Then we will describe various servers, and then also summarize several features of embedded systems. I just used the word embedded operating system to refer to embedded. Actually, it's just simply anything that has a computer in it, but you don't normally interact with it as if you are interacting with your general purpose computer. General purpose computer being like a laptop or a desktop computer. So mobile phone, will say, is an embedded device. It's not necessarily got a separate keyboard and everything, or big screen, or separate system unit. It's just meant to be like a mobile device, but over the years it's getting more and more functional, so you're getting more features, and it can actually operate in a similar way as most of the things that we can do on our computer. Things like train ticket machine, so various things that have computers sitting somewhere, but you don't necessarily use them the same way that you use normal computers. And there are a few other things that we'll cover as well, which is looking at the utility programs. So 2 things come out. We have the utility program, and then we have the operating system. And these are the 2 types of the system software that we'll be paying attention to. So we have the hardware part, which is the things we can touch, the things we can see, the things that are physically tangible. And we have the software part, and we know the software and hardware work hand in hand, right? So hardware gives the software platform to sit on, and also gives us things like input and output in terms of devices, or take the human beings into the digital world, whilst the software forms the world of the digital world. Like, I'd see it as a completely different dimension, but that's just my view. So the software part sits on the hardware, or through the hardware we're able to access the software. And the software, if we break it down, so we've got the hardware there, and we have software sitting on here. Just realize how horrible my handwriting is. So we've got hardware, software. And if we break the software down, we've got things like the commonly used, the applications that we run. So applications sitting on the layer that is close to where the user is, right? So let me draw my best art to get a stick man sitting down. So these are the things that normally user interact with, or the application softwares that we directly interact with or make use of most of the time. Then we have the operating system sitting between the software and the application layer and the hardware layer, giving us access to it or making it easier for us to use the hardware resources. We've got things like drivers. So mostly if you buy or if you get new hardware or new upgrades of specific devices, so let's say sound card can be maybe you buy a phone that is not in the mainstream, so it's just a smartphone. It can connect to USB, all right, but sometimes you need to install the drivers so you can actually connect your external device into it. So you can think of these things as the peripheral devices, so things that are not necessarily part of the original system unit or anything. So give us input and output access, or with additional features. Even mouse can be considered as a peripheral device. So if you are connecting peripheral devices to the computer, you need to have a set of code or low-level code that says, as far as this device is concerned, this is how it communicates. So maybe this is how the computer should read from it, or this is how the computer should write to it as well. And then you realize that your device will be identified because it's got its code that helps the computer to identify it. So it goes into the device drivers and then the utility programs. So utility programs, if you think about it as if it's programs that allow you to manage the computer, to manage other softwares, to control other things. So in that case, if you have like a very large file, right? So I have a very large file. It can be a video file, it can be a music file, it can be different files, and then you want to put them in one zip file. So it can be a zip file or a RAW file, right? You can make use of a software, some of the software like WinZip. You can make use of WinZip, or you can make use of something like WinRAR. Someone's microphone is on. If you can turn off for me, that would be very much appreciated. Or WinRAR to compress the files into a zip file and maybe like email it or something like that. So you've got one software managing other software's utility program. And also you have softwares like antivirus. So Norton Antivirus, most Windows comes with Windows Defender by default. So these softwares can scan through all your files and it can identify which ones have like viruses attached to them, which one could be harmful, and it can also isolate them from the rest of your computer by basically blocking access to these files. So similar such files or such software allow us to get access to other files and then look into them to see whether we can make decisions about them. So it's also also you can say that antiviruses are also utility programs. Then you can have other softwares like disk management softwares allow us to do partitioning of different hard drives. So you can partition your hard drive, give it different size. So you say your data file, where you want to store your data, maybe you keep 2 gig or 5 gig. And then where you want to keep your operating system, maybe you can keep like 3 gig. And then maybe you reserve one that you're not going to use for a while, or those kind of things. And then later you can delete partition, or you can even use to format external USB. So that's example of some utility programs. Then you've got interpreters and then translators as well. So we did watch this. I want us to watch it again, just a few minutes, and then we watch other things as well, just to allow flow of things. Can I double check with the class? Is everything okay up to this point? If okay, you can put in the chat window. If you have a question, please let me know. I'm sorry, I don't understand that language. Could you speak in a language I understand, so at least I can... I would emphasize that... That's very interesting.
Translator to translate it.
That's very interesting, but I think, yeah, I do agree with Faith. We do need a translator to translate all that. So it's just to check. So if no question, please put in the chat window no or yes, and whenever I ask, just do that, okay? So at least I can see those who are still with me, and then we can carry on. But thanks for muting yourself. Please, maybe you may want to use Google Translate or something, so we can at least get what you wanted to tell us. Or later, when we listen to the recording, we'll take it to an expert and they will translate for us as well. Or you can choose to translate yourself, and I know you can. So happy to move on then. Yes? Good. Amos said no questions, sir. Let's go with Amos option.
If your computer is on, the system software is running. System software is a computer program designed to run a computer's hardware and applications. Thinking of a total computer system as a layered model, the system software is between the hardware, or physical components, and user applications. System software runs constantly in the background, maintaining a computer's basic functions, including the disk operating system, file management utility software and OS services, and providing an interface for the user. The most common example of system software is an operating system, or OS, which manages all the programs in a computer, like Microsoft Windows or Apple's Mac OS, for example. But system software also includes the basic input-output system, the boot program, an assembler, a device driver, and other system utilities. Hypervisors, which virtualize computer resources, are also system software, which you can read more about by clicking the link above or in the description below. System software is generally high speed to provide an effective platform for higher level software, hard to manipulate, requiring a program language more difficult to use than an intuitive user interface, written in a low-level computer language that the CPU and other computer hardware can read, close to the system, connected directly to the computer hardware, and versatile, needing to communicate with both the computer's specialized hardware and the application software. What else can you name that's included in your system software stack? Share in the comments below, and be sure to hit that like button too.
So it's just a brief about system software, which is like similar thing as to what we've described in the previous session. And I did say with this one is that the good take home is that good take away from it is that the system software is constantly doing stuff in the background. It's constantly running in the background to make sure that it makes the use of the computer systems a lot easier for us. continue. We'll come back to it at some point, and then we have already highlighted two key ones, two types that we are looking at is the operating system and the utility program, or you can think of it as a utility software. So mainly it's just programs. You can think of them as a group of programs. Programs are codes written and put in an object format or in an executable format. So it's just a group of codes or programs that allow us to control or maintain the operations of the computer itself or the devices. So you can think of the devices as some of the peripheries around it. Yeah. Then I mentioned that because we'll be spending more time on the operating systems now, and we don't want to be thinking what is the utility program, we just want to have a brief about the utility program before we go on to the operating system. So here we did watch this yesterday, and with the key examples that came out was the Norton antivirus and also the various types of antivirus that you may use. The good thing is that you will all have access to this video and can watch in your time. It doesn't include audio at the moment, but you can watch it in your own spare time. But talking about the utility software, I explained it earlier, but you can think about it as a software that helps you to analyze. So when you're actually going through, like when the antivirus is going through files to check whether it's got a virus or not, and then to configure things like I've got a question. I will attend to it in a second. Things like the disk manager. The disk manager allows you to do some partitioning. It allows you to increase the size of a partition or also make it smaller. Optimize. There are certain softwares in like Windows you can find the defragmenter. And please mute your microphone. It will help the class a lot, unless you have a question. But do bear with me. I can see the chat now. I'll come back to the questions in a second. So it helps you defragmenter. If you've been using your computer for a while and you've been deleting files and everything, because in the registry it looks like you've got some spaces in it. The defragmenter just remove this the holes or spaces and put the files closer to each other so they appear in a more contiguous or continuous way, and your computer can actually run faster. It's just an example of it. And then you have other software that you can use to maintain your computer. And I mean, I did say that one example that I really like is a software from I used a long time ago. I don't know, about 12 years or 15 years ago, and it was called Easy Recovery, and it was completely free. But if you deleted stuff on your computer, did some permanent deletion, no more in your recycling bin, you could use that to recover these files that you have deleted. So example of utility program. So Deborah is saying that she's tried to open the files and she couldn't. So when I upload the PDF, the PowerPoint version, you will get all that. And again, I will try to include all the links in the slides as well. So I'll probably have to replace the PDF file. Does that help, Deborah? Thanks for letting me know.
Thank you, sir.
Thank you. So, what is the operating system? What does it do? So it's just basically a set of programs, and these programs are made of code and other things, containing instructions that work together. So the operating system works to coordinates all the activities among the computer hardware resources. How do we just put this in a different way? So you've got your hardware there, and you've got the application. So example, now we've got PowerPoint. Let's make it PP. And then we've got like Zoom, or I've got that. Got Zoom. From the hardware, I've got my camera on. Besides the actual computer itself and what's going on in the system unit, I've got my sound coming output. So sound out, So let's make it sound I/O. So you've got the input and output. So I've got my microphone and everything happening as well. And at the same time, I've got some PDF and other things running in the background, and I've got my browser open as well because we just did the attendance online. So all of these are requesting access to the processor. And remember, even the sound card itself as well will also need to have access to the processor, and everything or needs to have a processor need to have access to it to output to it. So let me put the IO in there. And the processor, if we're thinking about it as one processor without writing or anything, it's just doing one thing at a time. So it's looking at all of these one at a time, but it's switching between them so fast that it appears as if everything is happening at the same time. So it appears as if you can see me smoothly, you can hear me, and you can see the PowerPoint, you can see the presentation, but what is happening is all of these things are running one at a time. And even to give that access, to put it in a way that you can visually see them on your computer. Notice it's paused again. Don't know why it keeps doing that. My camera has paused, so just bear with me as I turn it off and back on. Yeah, so even the access to the screen itself that you are using to watch me, all these things happening in the background, you've got the operating system sitting there and it's doing the scheduling for you. It's like attendance management for the class. If student comes with queries, and the admin people are doing all that magic in there. They are coordinating student attendance. They are coordinating things like, do we have the right resources to teach? They are coordinating a lot of things in the background. So the same way that that the operating system is working in the background to give us access to the hardware, to make sure that hardware also get access to things that the user is requesting for, to make sure applications are running smoothly in the background and other things. So examples of some of the things that the OS does for us in terms of when to help you shut down and also boot your computer, to provide things like the user interface, to manage programs, memory management. So manage the memory, make sure that of course you don't run out of memory. Make sure that even if you're running out of memory, you can use things like virtual memory to compensate, to coordinate tasks, configure devices, configuration, establish internet connection, and that works also with control and network, hand in hand, monitor performance, provide utilities, and also updates. You've got automatic update of the OS itself, and then you've also got, if you're a Mac user, you get free updates, right? That is why some people prefer Mac, right? So updates, and then also give you a level of security. We did say that Windows have Windows Defender. At the same time, you've got like firewall and all those kind of things that you can make use of. Right, so it's the same features but presented in a diagram form, quite similar to what we just drew, and it looks like an octopus sitting in the middle, so it can actually control stuff, right? So very similar to the stuff that we just talked about. Before we jump into this, I want to pause and check whether everything is okay, or you have a question for me before I move on. Yes, no, maybe. Someone going to type in the chat window? Can I double check? Do you have a question for me? We carry on. Okay, good. So if you have a question, simply just type as we go. Hopefully you can hear the sound as I play.
Did you know that you and your computer speak different languages? It doesn't speak Spanish, or Swedish, or Chinese. It speaks in ones and zeros. You can't communicate directly with your computer, but that's where your operating system comes in. The operating system, or OS, is the program that lets you interact with your computer. Together, the operating system and computer hardware form a complete system that determines what your computer can do. There are many different operating systems. Two of the most common ones are Microsoft Windows and Mac OS. Windows comes preloaded on most personal computers, while Mac OS runs on all new Macs. Operating systems aren't just for desktop and laptop computers. Mobile devices run mobile operating systems, like Apple iOS or Google Android, which are designed for interactions with smaller touchscreens. Before downloading a new program or application, be aware that it may not be available for your operating system. Some applications work on all devices, while others only work on certain ones. So get to know your operating system to see how it works and what it can do. GCF Global, creating opportunities for a better...
Right, so here's the question. What are some examples of operating systems? Examples of operating systems. Give me some example. Any example? Windows operating system. Who was that? I owe you chocolate. If you're ready.
iOS.
Macintosh.
Yeah. The two iOS and someone says something else. Android. More? There's the Unix operating system. Ubuntu. I love Ubuntu. Yeah, Ubuntu is a Linux operating system.
Ubuntu. Yeah, Linux.
It's completely free as well. And you know what? You can actually download the code for the operating system, and you can also contribute to it. So we watched something on how the Unix became so popular. Mac and Linux both based on Unix as well. So very good. And then of course there are several operating systems and other things, but mostly still some of them coming from Windows and other things.
Sorry.
Please ask.
So, is it possible for someone to upload operating system of an iPhone into an Android?
You want to upload the Apple iOS into an Android phone?
Yes. Is it possible?
I think the question is quite similar to saying that you've got, let's say, a Dell laptop and you want to install an iOS on it. So when it comes to dealing with software, this will be my unofficial answer. Normally, anything is possible just because hackers with good abilities can get something installed. It doesn't mean that it will run smoothly, but ideally it shouldn't be possible. So if you've got, you can run things like a virtual machine that can help you to install certain operating systems and then sort of run from it, from main computer devices. If it gets to mobile devices, it's a lot more tricky because the hardware stream has been, the desktop stream and laptop have been around for quite some time. So most of the common devices, you find easy drivers for them, or you find versions of the drivers for them to work. My concern is even if you manage to jailbreak, blah, 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 do whatever to install stuff, you find your hardware components will not work properly. So unless you have done it before and you want to tell me that that has been done, I will say without
No,
because if you notice on Apple computers, and I'm talking about the computers, you can do dual boot. So basically you can have two operating systems on it and they call it boot camp. So you can use boot camp to install Windows on a Mac machine. Right? Quite similar to when you are logging in and then you run it. But Apple is quite particular about, because definitely their operating system, custom made for their Mac machines. So they are quite particular about making things easily accessible for other types of devices. So if you notice, if you want to build an iOS app, for example, a couple of years back, you have to buy a Mac computer because Xcode only runs on Mac machines. It wouldn't run on anything else, let alone the operating system. Does that make sense? Yeah. So it may take a lot of work, but even that, I doubt most of your hardware will work properly with it.
Okay.
Yeah.
Thank you.
I hope that helps. Yeah. But if you do manage, please let me know because I'm interested to see how it works. Right? If you want to try that and you do manage to do it, by all means, let me know about it. It will be an interesting project. But I mean, I did mention about bootcamp and other things. Just know there's virtual machine that allows you to also run some other operating systems. And I think it's called BlueStack. With BlueStack, you can actually run Android on a desktop as well. But these days, if you use Samsung has like their own version of the software called Samsung Desk. Samsung Desk. I forgot it. I can find it. Yeah, you can run the Samsung software. You plug in, and you will just run your phone on your computer as if basically you are running your phone. You have like the Android running on your computer, but on the mobile device, I'll be careful. All right, so moving on, and soon we'll be taking a break. So those who are getting pretty tired, do know there's some good news coming. Right. So we are looking at a bit more about the functions of the operating system, just stepping a bit further into things, and we'll be looking at when you try to start your computer, what happens. And the process of starting the computer is called booting, right? So you have two options, cold boot and then warm boot. So I'm thinking, of course, if the machine is switched off and has been off for some time, it's cold, right? When your computer has been on for some time, the processor gets warm, so it feels really warm, right? Or somewhat more warm. And depending on what computer you're using or which year it's from, it can get really hot, right? So when you are turning on your computer for the first time, when it's being powered off completely, this is called the cold boot. So using the power button to just press it and put it on when it's off. And if it is already running and you are using the operating system to switch it off, then that is called the warm boot. So before we jump into this, because I want to talk more about the warm boot and then the cold boot, basically if you think of, you have a Windows machine and you press the Windows button and you type which will open the search bar for you, or you type shut down, and then the operating system shuts down your computer for you. That is the warm boot. Or restarts your computer for you, sorry. So shut it down and then it will start it up for you. So that's when it restarts for you. That's called warm boot. I'm gonna pause here and I will pause the record. So we've been talking about the operating system and well, basically system software in general, and then we had a bit about chat about utility software, and we've been looking at the operating system, and we got to the point where we looked at what happens when you turn on your computer or something like that, or some of the features, and then we basically just touched it a little bit by talking about the fact that we've got the cold boot and then we've got a warm boot. And warm boot is simply restarting your computer with the operating system. So simply clicking something like the Windows keyboard and then pressing shutdown. On Windows, you can just go to the settings and then you do shutdown, or for example. So on Mac. So let's carry on, and I would want you to watch something a bit more on your operating system. So this woman, I mean, in my opinion, can talk really fast, faster than I can. So if, let's say, it's a bit too fast, let me know if you want me to play some sessions again. But the key thing is that you've got access to it, and someone did say they struggled to watch the video, so I'll provide you the link as well.
This episode is supported by Hover. Hi, I'm Carrie Ann and welcome to Crash Course Computer Science. Computers in the 40s and early 50s ran one program at a time. A programmer would write one at their desk, for example, on punch cards. Then they'd carry it to a room containing a room-sized computer and hand it to a dedicated computer operator. That person would then feed the program into the
Thanks for letting me know. You can't see the screen. Thanks, Tochi. Was spotted. Right, let me bring it up. I do apologize for that, but hopefully you can see my screen now. Just gonna start again.
Hi, I'm Carrie Ann and welcome to Crash Course Computer Science. Computers in the 40s and early 50s ran one program at a time. A programmer would write one at their desk, for example, on punch cards. Then they'd carry it to a room containing a room-sized computer and hand it to a dedicated computer operator. That person would then feed the program into the computer when it was next available. The computer would run it, spit out some output and halt. This very manual process worked okay back when computers were slow, and running a program often took hours, days, or even weeks. But as we discussed last episode, computers became faster and faster and faster, exponentially so. Pretty soon, having humans run around inserting programs into readers was taking longer than running the actual programs themselves. We needed a way for computers to operate themselves, and so operating systems were born. Operating systems, or OSs for short, are just programs, but special privileges on the hardware let them run and manage other programs. They're typically the first one to start when a computer is turned on, and all subsequent programs are launched by the OS. They got their start in the 1950s as computers became more widespread and more powerful. The very first OSs augmented the mundane manual task of loading programs by hand. Instead of being given one program at a time, computers could be given batches. When the computer was done with one, it would automatically and near instantly start the next. There was no downtime while someone scurried around an office to find the next program to run. This was called batch processing. While computers got faster, they also got cheaper. So they were popping up all over the world, especially in universities and government offices. Soon, people started sharing software, but there was a problem. In the era of one-off computers like the Harvard Mark I or ENIAC, programmers only had to write code for that one single machine. The processor punch card readers and printers were known and unchanging, but as computers became more widespread, their configurations were not always identical. Like computers might have the same CPU, but not the same printer. This was a huge pain for programmers. Not only did they have to worry about writing their program, but also how to interface with each and every model of printer, and all devices connected to a computer, what are called peripherals. Interfacing with early peripherals was very low level, requiring programmers to know intimate hardware details about each device. On top of that, programmers rarely had access to every model of peripheral to test their code on. So they had to write code as best they could, often just by reading manuals, and hope it worked when shared. Things weren't exactly plug and play back then, more plug and pray. This was clearly terrible. So to make it easier for programmers, operating systems were implemented as intermediaries between software programs and hardware peripherals. More specifically, they provided a software abstraction through APIs called device drivers. These allowed programmers to talk to common input and output hardware, or I/O for short, using standardized mechanisms. For example, programmers could call a function like print high score, and the OS would do the heavy lifting to get it onto paper. By the end of the 1950s, computers had gotten so fast they were often idle waiting for slow mechanical things like printers and punch card readers. While programs were blocked on I/O, the expensive processor was just chilling, not like a villain, just relaxing. In the late 50s, the University of Manchester in the UK started work on a supercomputer called Atlas, one of the first in the world. They knew it was going to be wicked fast, so they needed a way to make maximal use of the expensive machine. Their solution was a program called the Atlas Supervisor, finished in 1962. This operating system not only loaded programs automatically, like earlier batch systems, but could also run several at the same time on its single CPU. It did this through clever scheduling. Let's say we have a game program running on Atlas, and we call the function print high score, which instructs Atlas to print the value of a variable named high score onto paper to show our friends that we're the ultimate champion of virtual tiddlywinks. That function call is going to take a while, the equivalent of thousands of clock cycles, because mechanical printers are slow in comparison to electronic CPUs. So instead of waiting for the I/O to finish, Atlas instead puts our program to sleep, then selects and runs another program that's waiting and ready to run. Eventually, the printer will report back to Atlas that it finished printing the value of high score. Atlas then marks our program as ready to go, and at some point, it will be scheduled to run again on the CPU, and continue onto the next line of code following the print statement. In this way, Atlas could have one program running calculations on the CPU, while another was printing out data, and yet another reading in data from a punch tape. Atlas's engineers doubled down on this idea and outfitted their computer with 4 paper tape readers, 4 paper tape punches, and up to 8 magnetic tape drives. This allowed many programs to be in progress all at once, sharing time on a single CPU. This ability, enabled by the operating system, is called multitasking. There's one big catch to having many programs running simultaneously on a single computer though. Each one is going to need some memory, and we can't lose that program's data when we switch to another program. The solution is to allocate each program its own block of memory. So for example, let's say a computer computer has 10,000 memory locations in total, program A might get allocated memory addresses 0 through 999, and program B might get 1,000 through 1,999, and so on. If a program asks for more memory, the operating system decides if it can grant that request, and if so, what memory block to allocate next. This flexibility is great, but introduces a quirk. It means that program A could end up being allocated non-sequential blocks of memory in, say, addresses 0 through 999 and 2000 through 2999. And this is just a simple example. A real program might be allocated dozens of blocks scattered all over memory. As you might imagine, this would get really confusing for programmers to keep track of. Maybe there's a long list of sales data in memory that a program has to total up at the end of the day, but this list is stored across a bunch of different blocks of memory. To hide this complexity, operating systems virtualize memory locations. With virtual memory, programs can assume their memory always starts at address 0, keeping things simple and consistent. However, the actual physical location in computer memory is hidden and abstracted by the operating system. Just a new level of abstraction. Let's take our example program B, which has been allocated a block of memory from address 1000 to 1999. As far as program B can tell, this appears to be a block from 0 to 999. The OS and CPU handle the virtual to physical memory remapping automatically. So if program B requests memory location 42, it really ends up reading address 1042. This virtualization of memory addresses is even more useful for program A, which in our example has been allocated 2 blocks of memory that are separated from one another. This too is invisible to program A. As far as it can tell, it's been allocated a continuous block of 2000 addresses. When program A reads memory address 999, that does coincidentally map to physical memory address 999. But if program A reads the very next value in memory at address 1000, that gets mapped behind the scenes to physical memory address 2000. This mechanism allows programs to have flexible memory sizes, called dynamic memory allocation, that appear to be continuous to them. It simplifies everything and offers tremendous flexibility to the operating system in running multiple programs simultaneously. Another upside of allocating each program its own memory is that they're better isolated from one another. So if a buggy program goes awry and starts writing gobbledygook, it can only trash its own memory, not that of other programs. This feature is called memory protection. This is also really useful in protecting against malicious software like viruses. For example, we generally don't want other programs to have the ability to read or modify the memory of, let's say, our email. With that kind of access, malware could send emails on your behalf and maybe steal personal information. Not good. Atlas had both virtual and protected memory. It was the first computer and OS to support these features. By the 1970s, computers were sufficiently fast and cheap. Institutions like a university could buy a computer and let students use it. It was not only fast enough to run several programs at once, but also give several users simultaneous interactive access. This was done through a terminal, which is a keyboard and screen that connects to a big computer, but doesn't contain any processing power itself. A refrigerator-sized computer might have 50 terminals connected to it, allowing up to 50 users. Now operating systems had to handle not just multiple programs, but also multiple users. So that no one person could gobble up all of a computer's resources, operating systems were developed that offered time sharing. With time sharing, each individual user was only allowed to utilize a small fraction of the computer's processor, memory, and so on. Because computers are so fast, even getting just 1/50th of its resources was enough for individuals to complete many tasks. The most influential of early time-sharing operating systems was Multics, or Multiplexed Information and Computing Service, released in 1969. Multics was the first major operating system designed to be secure from the outset. Developers didn't want mischievous users accessing data they shouldn't, like students attempting to access their final exam on their professor's account. Features like this meant Multics was really complicated for its time, using around 1 megabit of memory, which was a lot back then. That might be half of a computer's memory just to run the OS. Dennis Ritchie, one of the researchers working on Multics, once said, "One of the obvious things that went wrong with Multics as a commercial success was just that it was sort of over-engineered in a sense. There was just too much in it." This led Dennis and another Multics researcher, Ken Thompson, to strike out on their own and build a new lean operating system called Unix. They wanted to separate the OS into 2 parts. First was the core functionality of the OS, things like memory management, multitasking, and dealing with I/O, which is called the kernel. The second part was a wide array of useful tools that came bundled with, but not part of the kernel, things like programs and libraries. Building a compact lean kernel meant intentionally leaving some functionality out. Tom Van Vleck, another Multics developer, recalled, "I remarked to Dennis that easily half of the code I was writing in Multics was error recovery code. He said, we left all that stuff out of Unix. If there's an error, we have this routine called panic. And when it is called, the machine crashes and you holler down the hall, 'Hey, reboot it!' You might have heard of kernel panics. This is where the term came from. It's literally when the kernel crashes, has no recourse to recover, and so calls a function called panic. Originally, all it did was print the word panic and then enter an infinite loop. This simplicity meant that Unix could be run on cheaper and more diverse hardware, making it popular inside Bell Labs where Dennis and Ken worked. As more developers started using Unix to build and run their own programs, the number of contributed tools grew. Soon after its release in 1971, it gained compilers for different programming languages and even a word processor, quickly making it one of the most popular OSs of the 1970s and 80s. At the same time, by the early 1980s, the cost of a basic computer had fallen to the point where individual people could afford one, called a personal or home computer. These were much simpler than the big mainframes found at universities, corporations and governments. So their operating systems had to be equally simple. For example, Microsoft's Disk Operating System, or MS-DOS, was just 160 kilobytes, allowing it to fit, as the name suggests, onto a single disk. First released in 1981, it became the most popular OS for early home computers, even though it lacked features like multitasking and protected memory. This meant that programs could, and would, regularly crash the system. While annoying, it was an acceptable trade-off, as users could just turn their own computers off and on again. Even early versions of Windows, first released by Microsoft in 1985, and which dominated the OS scene throughout the 1990s, lacked strong memory protection. When programs misbehave, you could get the blue screen of death, a sign that a program had crashed so badly that it took down the whole operating system. Luckily, newer versions of Windows have better protections and usually don't crash that often. Today, computers run modern operating systems like Mac OS X, Windows 10, Linux, iOS and Android. Even though the computers we own are most often used by just a single person, you, their OSs all have multitasking and virtual and protected memory, so they can run many programs at once. You can watch YouTube in your web browser, edit a photo in Photoshop, play music in Spotify, and sync Dropbox all at the same time. This wouldn't be possible without those decades of research and development on operating systems, and of course the proper memory to store those programs, which we'll get to next week. I'd like to thank Hover for sponsoring this.
So yeah, I mean, thank you very much. I did say the warning well in advance though. She talks faster than I do, right? She talks very, 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 very fast. But then thanks to those who were putting stuff in the chat window to draw my attention to some things. But because you've got this link that you'll be using us, or you can do what I did, right? So basically, you can, it's a YouTube video. On YouTube, you can click these settings, and then you can put you can make it slower, like I just did, and also you can put the subtitles if you want, or the captions, right? If I saw it earlier, we would have sorted it out. But it's nothing to worry about at the moment. Just think of it this way. Laurie, if you've got a question, please ask.
Hello.
Laurie? Okay. Right. So you've got access to this and you can watch it again to understand what is happening. But the key takeaway for there are a few takeaways for me actually. I mean, I personally like this just because they've got access to some video records or some images that they can use to show about like initial things like the punch cards. So like when computers started, you can have a history of the mechanical computers and other things, but when it got to the point where we could actually program computers, so you have punch cards. It's like you think of it as a strip of card with some holes in it, more or less coding the ones and zeros that a computer instructions that a computer should follow, and this will be taken to a special operator for these computers, or someone who is trained to operate the computers, and that person will take the punch card, put it into the computer, and then it will run and bring out the output. So over time, it just became a bit so apparent that even though the system was a bit too slow, so people we will have the punch cards ready, and then they will go, and then it would take a long time before you get it printed out and everything. Then it came the idea of, why don't we come up with an operating system that would abstract the use of the hardware and also the application software that we want. Another issue was that as peripherals became more common, so peripherals are devices that can be connected to these machines, or special devices that can give a computer additional functionalities, right? So the computers were being made, manufacturers were coming with different things that can be different hardware that can be connected to the computer. To know how to use these peripherals, it sounds like you literally need a PhD, right? So you need some special training, you need some special understanding. So it was just becoming a bit too much, or a bit too cumbersome. So the idea of the operating system, one, to make it a lot easier for people to use it, and also of course to make it a lot easier to interface with peripherals. Then eventually they found out, wow, yeah, operating systems developing, people don't have to queue so much to make use of machines and everything, and at the same point the price of computers dropping. But the issue, one of the issues was that even though the operating system was becoming fast, it had reached a point where OS has become so fast that the processor was mostly sitting down doing nothing, because it was processing the inputs and outputs, that requests that were being it was getting much faster than it should, and other things. So pretty much, why didn't we come up with other alternatives, like have something like separate, add more features to OS to make it do things like multitasking and other things. So the multitasking comes in with the Atlas, and then because we want to do things like multitasking, Atlas OS coming up, we want to do things like multitasking, they needed more memory, so they needed to add additional memory. So they added things like special magnetic drives and other types of memory that were available then, so you can have more IO being processed at a time. Then the complexity was increasing, and the idea of Unix came up, and then Unix was like, okay, the Unix idea was, why don't we split the key functionalities of the OS into two? So the bits that deal with the core hardware management stuff, like managing the memory, managing multitasking and all those kind of things, we put it at the very lower level, we call it the kernel. Right, then we can have another layer, which is like the ones that will eventually interface with the application side. So if you see someone writing code, they will say we are doing shell scripting, right? So we're writing Linux commands to actually interact with the shell. Or if you've used things like Raspberry Pi before, or written a terminal code before, used Microsoft DOS before, and other things. So that separation also made it quite easy, and what they also did was to abstract the error codes that could potentially be received. Adibola, do you want to show us something? Was that intended for somebody else? Okay, so so yeah, that they reduced the number of error codes to just really one, error messages and other things to just really one, and that's made the code a lot smaller, which means it can be run on more machines. And then Unix became very popular, so around that same time you got a lot of compilers being written for Unix. Compiler means people could write their own code and compile on them. And also over time, things like Linux come out of Unix, and Linux is completely open source, meaning you can get a code and you can also contribute to the Linux community as long as you adhere to the licensing agreement and other things for the open source community or compliance. So that's sort of a summary of what she talked about. Can I just double check? At least I spoke a bit slower enough for you to get. Is that a yes? Good. So we're interested in what happens when you boot your computer. So you plug in your computer, you press the power button. First thing that happens, electricity goes into the power supply and it sends signals to components of the system unit. And with regards to the system unit, we're referring to this whole system on there. Of course, you've got a chassis, you've got a motherboard, and you've got some things connected on the motherboard. This is what I would say, caution with using when you're touching power supplies. If you're anything like me and you like to play with these sort of devices, open them up to tinker with them, please. I mean, I had a really terrible experience with dealing with the power supplies. They usually, especially these ones, they usually come with large capacitors. Capacitors can store electric charge. So if it's been recently plugged in and then you're just opening it and you're going to touch the power supply, just be extremely careful, because I had an extremely big shock. Okay. Today is that day, right? Just bear with me as I find a way to mute everybody. Thank you. Right, so after you plug in and then you've got the electric signal going through the other parts of the system unit from the power supply, through the power supply, the processor will find the read-only memory, right? It's a read-only memory chip. And in this particular read-only memory, it actually contains the BIOS. And the BIOS is the basic input and output system, right? So what is this basic input and output system about? So on your hard disk, you've got your operating system code sitting on there, right? The processor needs to find out, okay, so one, what is the right boot sequence? Where is the operating system loaded? Which particular secondary storage device will I find the operating system on? How does the system administrator want to format the machine? So which device does he want me to look first in? So if you've ever tried to format a machine before from a USB, sometimes you need to go into the BIOS setup to change. I see a chat coming up. Okay, Abigail, if you've got a question, please just type. So to change the boot sequence, for example, so in that case, if you want to format from a USB, you put the installation file or the bootable operating system on your USB, you change the BIOS setting. When some machines, as it's coming on, you press like Control F10 or F2, and you keep pressing F2 will take you to the BIOS. Just an example, depends on the machine you are using, and you can configure the boot sequence so you get like the USB first, hard drive second, maybe network command or something following up later. So it tells just some basic configuration. Sometimes you can actually use the BIOS to also lock the whole system so people cannot have access to it. And of course, you can put password on your BIOS so people cannot change it. So it knows where to load through the BIOS. Then the step 3, the BIOS will perform something called post, which is power on self-test. It's like self-diagnostics to check some basic components. And these components, like, do you have a mouse? Do you have a keyboard? Or are the adapters working properly? And how would it know that? It compares it with the content of a CMOS. So, right, with CMOS is just a chip. Just think of it as a special microchip. You've seen these spider-looking things, right? They're mostly black color chip. So it compares the results of the post, what is the power and self-test, with the data in a chip to make sure if everything is okay to progress. So from that step, the BIOS may also look at the system files, and this is where we talked about the boot sequence. So it may look for things like, where is your operating system? Is it on a flash drive? Should I look at a flash drive first? Should I look at like an optical disk drive? So you've got your disk drive there. Should I look into an optical disk drive? I know yesterday some of you did some questions which asked which of these is an optical device, right? And also it may also look on the hard drive. So, but mostly most people, after when they are not formatting, will set the hard drive first. So at least it looks directly from the hard drive. Then the system file, which is the OS, and the kernel, we did mention kernel a few minutes ago, the lower level of the operating system, which is closer to the hardware, if you say it that way, of the operating system will be loaded into the random access memory, because we know the processor is constantly interacting with the RAM or main memory. I think there was a question on what is RAM as well. Okay, so the operating system then will configure like things like information on the screen or how to do things, and also it may request information as that's several in the background process. It may even ask you to put in password and all those kind of things just when it's done, and then of course it will display on the screen. So these are sort of the basic things that go on in the background. So key things sitting in the power part, easy to remember. Remembering that the BIOS is actually a read-only memory, because this is very significant when a significant part of the startup process. So you don't want people writing over the BIOS. But I know that especially things like game consoles and other things, when people wanted to play different games that are not designed specifically for a certain game console, they will go and flash the BIOS or something like that. So sometimes people can actually like to play with these kind of things, like some of the questions we've had earlier about installing different operating systems and other things. So some people can reset it and put different stuff on there to make it sort of work in ways that is not intended. But that's hardware hacking, not what we are here to talk about anyway. Right, then you've got a post happening, and then from the post, content compares to CMOS, and then you have also things like loading the operating system itself from secondary storage, and then loading the basic part of the OS, the kernel and other things, and the high level part, things that we can say. So then we're talking about, I did mention about the boot disk, or you can call it about boot drive or boot files. So the boot drive, if in the previous case mentioned, mostly the boot drive would be like drive C or your hard disk, and you can also have like a memory card. Let me see my drawing of memory card. That's horrible, right? You can have a memory card or any external storage device or even internal storage device, and that is where your computer will start from, right? So you boot from your boot disk or the boot drive, and then you can have things like the recovery drives, which contains the system files, but that start the computer. But these recovery drives, I think if you're using HP, I believe it's either again F2 or F10. And most machines will, if you Google the machines make and how to get into the recovery mode, you can actually use a hotkey whilst you switch on the machine, and it will go into that page for you. And if, let's say, you've lost something, or you just want to reformat your computer, or you just want to reset it to factory reset and other things, you can make use of the system file information or the initial setup information stored in this special disk, and mostly it's just a small partition on your hard drive, and it will load or reset the machine back to the way that you got it the very first time if you got it new. Does it make sense so far? Yes? Yes?
Yes, sir.
Oh, wonderful. I like it when people talk.
Yes.
Thank you very much. Right. So mostly that's where you find the recovery disks, and then you make use of the recovery files that you want. So a bit more about the functions of the OS, and I like this hibernation mode. So I'll just jump straight into that first, because the first time I found that feature, I was extremely excited, because now, of course, everybody's safe to the cloud and everything. So in hibernation, you can actually put your system in the any documents that you have running, or software or things that you have running. You can basically just put your computer in a state where it can basically come on and come back on, and you have everything running in the same way that it was before. So it saves all the open documents and the programs on your hard disk before turning off. So it's pretty much saved the states. But even if you're a Mac user like me, if you switch off your computer without actually going through hibernation and other things, setting it up to go into hibernation after 5 minutes or something like that, once you put it back on, let's say if you open Chrome is going to try to restore everything that you had opened before, for example. Then there is the sleep mode. Sleep mode helps you save energy by just simply putting it into your machine in a low power state. Okay. So it's just putting your machine in a low power state. It's not really turned off completely, but it's just putting the machine in a low power state. So basically it saves and open documents in the run and on the turn off all the needed functions. Just simply the bits that are not being used are just being cut off. So the processor will be less busy, and then hence it will be in a low power stage or consume less power. Right, so more about the functions. We've seen the user interface. We are making use of user interface already. Things like Zoom that you're using and other things. Then we have the graphical user interface. We'll talk about the graphical user interface in a minute. So the user interface controls how we access data. So basically how we enter data, instructions that we give into the computer, and then also how we tell the computer to display things. And I'll just say the things that you can see how you actually get into the computing world, or how you get information from the computing world or from the digital world, if you see it as a portal or a different dimension like I do. Right. Then the graphical user interface, when something is graphical, basically you can more or less see, drag and drop, right click. You can just visually see how the thing is laid out. So we've got something graphically before us, like on PowerPoint, we can actually see some images and then some links and other things that are tangible to us that we can interact with. So things that for graphical user interface, they basically have menus. You can go to File, Save, Click, and other things. And also they have visual images. So things that we can see with graphics. Then you've got things like the command line interface. So if you have Windows and you press the Windows R, you can run, and then you open a small link for you, and you type CMD and then press enter. It will come up with a command line interface, or people will say the bash interface for Windows or Linux, or you also find the terminal window for Linux, terminal window for Mac as well. So the command line interface, basically you're not really seeing graphical representation. It's just a blank screen with some text that you type in, and then you delete text. Bless you. It's the wrong year to be sneezing though, so I do. Someone was sneezing, right? Could see that. All right, so continuing from there, just kidding. You've got the command line, which is basically interacting with the computer via text and other things. You can just simply, I can show you the command line interface on Mac if you want to use, and it's mostly the use of keyboard to enter the information. So in terms of how the operating system program directly affects your productivity, so what does all this mean to you, right? As a user, or what does it mean to us? It allows things like single user, so you can log onto your computer, you can create only one account for your computer, log onto the computer, or you can have like share computer with your friends and family, so you get your own account that you make use of, and when you are ready, you can either sometimes switch user, or you can log off one user completely, so each user, when they log onto the machine, will see different softwares they have installed or different interfaces. It's almost like if you use Netflix, it's like having several user accounts on Netflix, right? So each of you, when you log on, you do have your own interface to deal with, right? So you do have things like special delivery. You do have things like if you like watching more action movies, you see more action movies on your site and other things. So the multi-user just simply one single user on account, or and help you manage several users with different install things and other things. Then you can have things like making use of multitasking, or running several tasks at the same time. We are familiar with single tasks, so multitasking help us to seamlessly see applications, things that we are running, for them to appear as if they are running at the same time. Then we have things running in the foreground and things running in the background. So at the foreground in here, I've got like PowerPoint that you can actually see. And then in the background, there may be something like maybe an antivirus constantly running to check out things, or something like maybe the Zoom running in the background if I have it open. If I have a Word document open, that's also running in the background because we're not seeing it. And here is the preemptive multitasking. So multitasking, the idea of running several things at the same time. But preemptive, something like if a task with a higher priority comes in, it will stop the current task that is supposed to be running depending on what set of rule is set to follow. So the important task will run each time. So you notice PowerPoint is running and everything, but each time I press my mouse, it responds to it. So the mouse in here has something like a higher priority. So it's preempting, it's removing, like it's running instead of what was running before. So when it finishes, or depending on the rule set or the protocol set, the next task can run afterwards. So if you've got multi-processing where you have several processors, so running at the same time in the same chip, so you can have processor 1, processor 2, and these things can normally use for with multitasking to run things in parallel to make the computer work in a much faster or in a lot better way. So just example of stuff to show what the foreground applications are, some things running in the background and other things in the buttons and the interfaces and applications that we can run. Okay, so one key thing here, we did see a little bit about virtual memory with that woman who talks really fast on the video, but when she talked about virtual memory, what she described was maybe you've got an application A, so let's call it application 1, and then you can have an application 2, and again you can have application 3, and then the address that in memory that application 1 may be loaded, let's call this maybe 900, right? Then application 2 may be loaded into 1000. But because of multi-threading and multitasking, application 1 may be running again, or part of application 1 may be running again at maybe 90,000, address 90,000, for example. Again, my camera has frozen, so just bear with me. As soon as it comes, I will fix it. Right. That looks like good. So it's not in a very continuous way, right? The address of A1 and then A1, the second version, it's like 900 and then up to 90,000. So we can put a virtual address, which is an addressing system that is not really, it's not really real. It just maps to this. It's like a book reference, right? So in this case, this can start from 900. That's the address we will use. And let's say if the next one is 1000, it will give this one address 1000. So it kind of appear as if 9000, their physical address 9000 is actually continuous from there. So they run together. That is one type of virtual memory addressing. You can call it virtual memory addressing. But at the same time, there is something called virtual memory in general that has to do with if my RAM size is about, in terms of my memory size, if this memory size is like 1K. So 1 kilobyte worth of memory. And let's say I'm running a game that takes 2 kilobytes worth of memory, and my hard disk is about 1 terabyte. I can borrow some small part of my hard disk, which is an additional 1 kilobyte. So it appears as if I actually have, so it's just borrowed part of this hard disk, 1K from there, to add to my RAM. So it appears as if my RAM is 2K and big enough. So we have, let me put game there. So it appears as if it's big enough. But because that additional 1 kilobyte of memory that we are gaining is not real, because it's only virtual. So we call that concept virtual memory. that helps to understand, and I'll just read a bit more details into what the actual written concept is, right? So the operating system can it can transfer the recently used data or program instructions from memory to the hard disks when it's needed by the RAM for other things, right? And in step 2, the hard disk also can transfer these instructions from the hard disk to the RAM. So it's just simply RAM appearing as if it's bigger than it's meant to be, and then it just becomes virtual memory. But the problem with virtual memory is that the RAM is faster than the hard disks, right? So RAM is faster than hard disks. And because RAM is faster than hard disks, and the two are being combined and they have to appear as if they are continuously running together, the virtual memory is a lot slower than RAM working on its own, or the hard disk working on its own as well, because we have to have some interpretation of the address the same way we do with the virtual addressing system. So I would like to bring the session to a close here. I'll pause the recordings now and I will make